Okay. What are some estimates? Okay, this is 5.1. Okay, some of the estimates were what? Okay. 151 what? Meters. Okay. Anybody else? I can tell you that's not correct. So. Okay. Anybody else? Anybody else? Briar, what did you get? Okay, yeah. So what did you say? Okay, so which one are you going to tell me? Okay. Okay. The largest you didn't get? Okay. Anybody else? Anybody else? Caroline, what did you get? Just tell me what number you got. None of these seem to correlate at all. So it's not like yours is going to be right or wrong. It's dependent upon what these numbers say. Okay, so what did you do? Okay. Great. Okay. Anybody else? Emma? What did you get? Okay, well, what was your estimate? Because the first question was just like, what is an estimate? Okay. Okay. 49 for what? Okay. Alright, so I guess it didn't say it. Yeah, it did. To estimate the distance, and then it said what's the smallest and the largest reasonable estimate. Okay. So technically, if you say that my smallest estimate is going to be 0, it doesn't go anywhere. Is that an estimate? Yes. Is it reasonable? No. I would say no. So if we're talking about the smallest reasonable, here's how we're going to think about this. Let's say from time 0 to 1 second. We know at 0 times 0, the thing or he or person or whatever was moving at 3 meters per second. So let's say that this person, let's say this person moving, was moving at 3 meters per second for like almost a whole second. And at the last possible instance, magically, because you know this really isn't physically possible, magically, they started going 5 meters per second. So for 1 second, so at time 0, let's see, they were going 3. I don't want to do that. I don't like that. Let's count by 2s. 2, 4, 6, 8, 10, 12, 14. Okay. From 0 to 1, this person was going 3. I don't know why. 3. There. I don't know. I'm confused. Almost for a whole second. At the last minute, jumped up to 5. And then went 5 for like almost a whole second, and then jumped up to 14. And then went 14 for like a whole second. Okay. Is this possible? Not really, but this would be a good smallest estimate, right? It's the smallest reasonable, right? We can convince ourselves that this could have happened, right? Okay. It's impossible because I am calling this a person moving. The problem really didn't say that. The problem didn't say that we're confined by gravity or friction or any of those things. So in my example, you couldn't do that, but in some really weird, no friction, gravity-less place, could this happen? Do I? Theoretically. Theoretically, do you think this is the smallest reasonable estimate? Yes. Okay, what is our, how is this going to play out? So we're going to have 1 second times 3, because they went 3 for 1 second, plus 1 second times 5, plus 1 second times 8, plus 1 second times 14. Do we add the 22? No, because he just, like, after the second, like, jumped up to 22 at that very last possible instant. So he really didn't go to 22, right? For any substantial length of time. All right, so this is going to be what? 16 plus 14. Is it, I think. Excuse me, thank you. All right, now, what was the largest reasonable estimate? Well, it's going to be the opposite, right? It's going to be that he started at 3, but like instantaneously jumped up to 5. It went 5 for a second. And then instantaneously jumped up to 14, and then went 14 for a second. So that would be 1 second times 5, plus 1 second times 8, plus 1 second times 14, plus 1 second times 22. What would that be? 17 plus 22. $36 plus 8 is 44 plus 5, 49. 30 and 49. So question, how did you get, some people tell me how you got some of these. Who are brave. For what? Rate times time. Carolyn. Oh yeah. Numbers, yeah. I don't know. Like, we've only talked about this lesson for like 5 minutes. So let's we're gonna talk about this concept for like 2 weeks. So let's like stick with me. I can imagine you're one of those people at the movies that's like, I have to know what happens at the end and just be able to sit and enjoy this. Okay. Okay. Let's figure out what happened. Okay, there is some, let's say that this is a person walking. Okay, if this is a person walking, that means that they're walking continuously, they're walking They're walking differentiable, so this is like, there is a function. There is some nice function that's describing how they're walking, and let's say that it's increasing. So we know that at 0 their velocity is 3. So I'm going to count by 5. So their velocity at 0 is 3. Their velocity at 1 is 5. Their velocity at 2 is 8. The velocity at 3 is 14. And the velocity at 5 is 22. Or 4 is 22. I don't know why I cannot speak to it. Okay, so we see that it looks like let's make this a smooth curve. Let's say that this is our smooth curve. This is how the guy who's walking, he's speeding up. This is what's happening. Although 22 meters per second is probably pretty fast. I think he's driving. Let's say that he's driving. Okay, driving sounds a lot better. Can anyone of you walk 22 meters per second? I want to see that. Can you run 22 meters per second? 22 meters is like the length of this classroom.
22 meters is not the length of the classroom.
Okay, the 100-meter record is 9 seconds. So that person runs 11 meters per second. So yeah, you're right. Okay. So this person is driving. Speaking of which, are you doing track this year? I say, what's up with this tennis mess? Golf. Okay, anyway. All right. So I don't even know how I got off on that. Okay, so here's the graph. Here's what we did. We found these little rectangles, the area of these little rectangles. This is what I was actually just showing you. We found that one first. What did we actually estimate? We found, no, don't think in math terms. I'm just asking, like, in real life, what did we do? We found the areas of all of these. So what did we actually estimate?
The total velocity.
I don't want you to say any math word.
Oh.
Yes! Very good. We found, okay, now be a little more specific about what did we find about the space below? We found the area. See, I said she could use one math word to better describe what she meant about the space. Thank you. I got this. I'm going to go across the hall and tell Miss Rich you do not have your assignment on time. Okay. We estimated the area under the curve. Did he? That I actually probably believe. Okay. We estimated the area under the curve. That's what we did. Now, I'm gonna make note of this now so that in 4 weeks we can come back and I'll say, you remember that day that I said, okay, here's the day I'm saying it. What we found about this area under the curve was actually we took the velocity and we found the total distance, and the total distance was the area under the curve. I don't even know what that means. So say it again, I might have to poke you in the eye. What is with you people today? Y'all are so brazen. I don't know. Okay, so the relationship here, what'd you say? Oh, we are recording. I totally forgot. And I threatened you in the recording. I have to take it down. Okay. So the velocity, we got from the velocity to the total distance traveled. We estimated the distance traveled, and we found that was the area of the curves. These are kind of like all connected. So we're going to come back to this eventually. Okay, now back to this estimate of the area under the curve. What we actually found is called a Riemann sum. See, the two big problems in calculus, way back when calculus was being discovered or invented, whichever way you like to think of it. Way back when, there were two sort of things happening. One group of people were working on differential calculus, which is what we talked about, the slope of the tangent line. How do you find a tangent line at one point? The other group was working on kind of what we're shifting to now is this idea of area under the curve. And how do we find the area under a curve? And Riemann said, hey, I don't know, but I have a way to estimate it. Look, we can draw these little rectangles. And we see that these little rectangles estimate the area. Do they estimate it well? What would make it better? What would make the estimate? Okay, using rectangles, how could we make this approximation of the area better? So that's also what we did. I don't know if this is going to show color, but we'll try. This pen doesn't ever work. I'm not sure why. I always try it. I have faith. No. I got it. Thank you, though. The other thing we did was we said, okay, for the first second, he's going to jump up to 5 and then go 5 for a minute. And then he's going to jump up to 8 and go 8 for a second. I don't know why I said a minute. And he's going to jump up to 14 and go 14 for a minute. And he's going to jump up to 22 and go 20. I did it again. Go 22 for a second. So now we have all of this area to the curve. Does that estimate the area?
No, because you have all the
Well, it does estimate the area. Does it estimate it well? No. What would make it better?
If you have half of that. You add half of that extra one. Take the one on top. That's what you just said.
No. Yes and no. Okay, yes, you're right. It would make it better in this case. If we try to generalize this statement.
What if you do what I suggested earlier in draw four on the rectangle? So like just here, if you drew like a, and then you like went up, and then this one, you get the whole thing. No, you get the whole thing. Yeah, but
You wouldn't actually get the whole thing. You would still have spaces. Okay, anyone else? Does anyone else have an idea?
not Emily.
The area under the curve. How can we get a better estimate using rectangles? This is not rocket science. What? What? Use smaller rectangles. That is so smart. Why didn't you say it earlier? I just broke my pen. It just came to you? Are you telling the truth? Or are you being a little facetious? Okay, let me show you something. Okay, here we go. Here's the deal. Let's hide this because I want to show you. Okay, this from A to B, we're talking about the area of the curve. Notice that the little shaded, all the shaded is the area of the curve.
Is that close to you?
No. Okay, so here we're trying to estimate this. We're going to use 4 rectangles. So I'm going to use the left hand. We'll talk about this left, right, and best in a minute. But for right now, just know I'm going to draw 4 rectangles and do the left ones. Here's my 4 rectangles. You see that? Okay. So we're using left height. So we're starting at A, and we're using our height at A to draw the rectangle for however long it was. How long is this, by the way? B minus A over 4. Okay, so you take the distance and divide by 4 to get 4 rectangles. Okay, it does make sense. I know. It's weird. Okay, so here, now we're starting here, and we're going to choose this height to go however long with it. And this height and that. You see this, right? Okay, now, let's make more rectangles. Sorry. It's not so Let's actually keep making them. See, okay, look, we're making more rectangles. What's happening?
They're getting smaller.
More covering more.
It's getting better. Like the estimate is getting really good. It's not normal. Don't talk about that. Okay, look what's happening, y'all. You're gonna miss it because we're talking. Look, but you see how some of them are over the curve? Yeah, some are under.
Take over it.
Some are under. Look, it's not equal. Okay, let's do this faster.
What about in ours?
Wait, I want to get all these down. Okay, now we're doing this by 5. Okay, look. Okay. Look how sounds like a little bit like a Trelawney from Harry Potter. She's like my hero. All the serious and all into her subject. Okay, so anyway, do you see? It's getting closer. Like, okay, so we're talking about if we keep adding more okay, I have to stop this because you're not listening. It's like mesmerizing. If And so we keep adding them, and the area is getting closer and closer and closer. What does this remind you of? A limit! A limit! So maybe the area under the curve is defined by the limit as what happens to these rectangles. As the number of rectangles approaches infinity, or as the width of the rectangle approaches zero. Isn't it exciting? Yeah. I think that's what you get for Okay, so these two ideas, these two major calculus ideas, slope of a tangent line and the area under the curve, are both defined by limits, our favorite little limits. So we see that if we could let the rectangles go to infinity, we would get that. Okay. Yeah. No. Right? Okay. So these are called Riemann sums. We have left-hand Riemann sums and right-hand Riemann sums, and this is how we would note that. So L4, by the way, if you go back and watch the video, you will see what was on the computer screen, which is kind of cool. So, of course. Okay. L4 is going to be a left Riemann sum with 4 subintervals. That's how we would denote that. The left part means that you're going to choose the leftmost endpoints to start with the heights. That's what we did here. This was actually a left-hand Riemann sum with 4 subintervals. If we go back to our data here, this was our interval 2, 3, 4. There's our 4 intervals, but for this one we chose to use the leftmost, or the smallest of the heights. Does that make sense? That's why we left off 22. Because for this interval, we want 14 to be the height. Now, when we went back into the other way, the right-hand Riemann sum, then we're taking this interval, and we're going to do that by 5, multiply by 5, since that's the higher, or the right-hand interval. Okay, so this was our right Riemann sum, and like I said, the little number just denotes how many sub-intervals you need in your interval. Okay, so let's do this with a function, because that sounds like so exciting. I know you're thrilled. When calculus starts coming together, it's like my favorite thing. So yeah, for the next quarter or so, it'll be Who told you that? Okay, really? If it was, you should consider the source.
Because we don't understand you. Actually, like, one of your told me that. Like, that they heard that. Like, I don't know.
This is sketchy. Okay, looking back at this, we're going to finish this. We're going to finish this, because this is going to be like a 45-minute video, which is going to be terrible. We're going to finish this. Okay, here's our function, x squared plus 3 from 0 to 4. Here, I want to find L4. I'm going to draw it just to give you a visual of what's happening. X squared plus 3 looks like this, sort of. That's not very curvy. Okay, here's my subintervals here. Since I have 0 to 4 and I want 4 of them, then that's really convenient. They're all one length, right? Okay, if I'm doing a left Riemann sum, then I'm going with the left endpoint to be my height. So we have these rectangles that have widths and heights. Okay, and then this would be my next one, then this one, then this one. Okay? So L4 is going to be the width of my rectangles. Now, if they're all the same, you can always factor this out, which is what I'm about to do. The width is 1, I'm going to factor it out. And then I need the heights. What is the height at 0? 3. What is the height at 1? 4. What is the height at 2? 7. What is the height at 3? 12. Do I need any more? Why didn't I do the height at 4? Because I'm doing a left Riemann sum. Okay, so this is going to be what? 19 plus 3, 22 plus 4, 26. Yeah. Okay, now what if I want to do R4? Again, I'm going to just factor out the width, which is just 1. And I'm going to use the rightmost height. So actually I can just use the little thing I've already started. 4 plus 7 plus 12. And then I'm going to need the height at 4, which is what? 19. What is that? 19 and 19 is 38 plus 4 is 42. Is that right?
Oh wait, I can turn it. You plug in like 1, 0,
Yes.
1, 2, 3, 4.
Yes.
And the little function thing. And then you get this answer and like add them all up and that's why
That's exactly where it is because yes.
Get everyone?
Hey Reese. Are you good really? Is everyone good? Okay, what if we wanted to do L8? Okay, visually that's gonna, I actually can't draw it on the same one. That's unfortunate. So here's our graph again. Now this time I'm still using left heights, but I'm only going to go to half of this. Then draw this very good.
Is it ever going to not be L?
Okay, I'm just trying to show you what would happen. So now we have more rectangles. What are the widths of all the rectangles? Half. Remember I told you it's b minus a over however many subdivisions you have. So 4 divided by 8 is going to be a half. In case you are having trouble figuring that part out. Okay, we'll go over it. Just, if I have 8 subintervals, I'm going to have 8 rectangles. What are the widths of the rectangles? Because we're going from 0 to 4.
Oh, got it.
See right here, 0 to 4.
So the equation is b minus a over
The number of subintervals, which we usually denote as n. But yeah. Okay, now we need the heights. Here's how you get the height. My first height is going to start at 0 because this is a left-hand Riemann sum. The first one is going to start at 0. So I'm going to plug 0 into my function to figure out what is the height at 0. 3. What is the height at 0.5? Well, it's going to be 0.5 squared plus 3. Plus the height at 1, which is 4. We already figured that out. Plus the height at 1.5, which is going to be 1.5 squared plus 3. And we're going to keep going. Okay, now. Conceptually, does everyone understand? Okay, I want you to get your calculator. I'm going to show you how you would do this with a calculator. Okay, there's 2 functions on your calculator that you might slightly be familiar with. One is sum and one is sequence. So sum adds stuff up, right? Remember when you were like in 2nd grade and you made a little chart of all the words that were like adding words and all the words that were subtracting words? Do you remember that? It's like my 2nd earliest memory, for whatever reason. I'll tell you later. Okay, so sum means add stuff up. Sequence means that you're going to have some formula for a sequence, and if you ask your calculator to find the sequence, it's just going to spout out numbers. Like if you do the sequence of starting with 1 and doing integers, it would be 1, 2, 3. Your calculator is just going to spout out integers. That's what it does when you ask it to make a sequence. What we are doing, we do want a sequence because a sequence is going to give us these numbers here. It's going to plug it in the function for us. Plug in 1, plug in 2, plug in 3, plug in 1.5, 2, 2.5, 3, 3.5. It's going to do that and generate all these numbers. But what do we want to do with all the numbers? Add them up. So to make your calculator do that, first of all, you start with the change in x. You start with the width of the rectangle. So we'll do L8. The width of our rectangle is 0.5, so we're going to want to hit 0.5. And then we're going to multiply that by what would be inside of our parentheses. Here's how we get that. Sum of a sequence. So again, the sequence part is going to spout the numbers. The sum operation is going to add them up. So we want the sequence, and then here's the syntax. You put the function, comma the variable, comma the start, the stop, and then the change in x. And we'll go over why all this works. Just bear with me. The hard part while you're writing this down is this part. This is the only part where you really have to think. Okay, so here's what the calculator does. It says, okay, sequence, great. What sequence do you want me to give to you? And you tell it, well, let's do this function. Like in our case, x squared plus 3. I want you to do x squared plus 3, but the calculator's like, well, where should I start? Where should I end? Right, so we're going to tell it, okay, do this, start at 0. Since we're doing L8, we want to start at 0, right? And then where are we going to finish? Well, what is the last number we want to plug in to find the height? And that's where you have to think. What would it be? It's not 4. Oh, 3.5. Because we're doing a left-hand Riemann sum. So our last height, we're going to plug in is 3.5. And then we tell it, okay, so great. You want me to do 0 and then stop at 3.5, but should I do like every 1? Should I do every 0.5, every 0.1, every 0.7? Like, what do you want me to do? And that's where you say, okay, yeah, 0.5. We want you to be plugging in 0, 0.5, 1, 1.5, all the way to 3.5. Does that make sense? Logically. Okay. So that's why we have change in x again. So go ahead and plug this in. So our change in x is going to be 0.5. Okay. So sum is in the catalog. Sequence is also in the catalog. It also might be under math, but I'm not sure. It is 29.5. Okay, go to second 0. Second 0 is the catalog. Is it in math? Does anyone know? Okay. Hey, if you hit the letter, if you find the S on your calculator, whatever button it is, and hit it, it'll take you to the S. Hey, just hit alpha S. Yes, you do sum, and it'll open this parenthesis. Then you go back to the catalog and find sequence. And then we're going to have x squared plus 3, comma x, comma 0, comma 3.5, comma 0.5, close all these parentheses. Second 0. If y'all are really good with your calculator and kind of smart, you can make a program that would automatically come up with all this for you. Did you? I used to know how to write programs, but not so much anymore. You can hit alpha S, and it'll take you. Yes. Hey, sum is in math, y'all. I think it would be the same. I think. Okay, if you did this, I want you to do R8. If you're done, do R8. So you think how you would take what you just learned and apply it to R8. See what you get. It's by the parentheses. Hannah, it's by the parentheses. I don't know.
I got errors in
Okay, so for R8, listen. For R8, this is how how it would change. You get 0.5 times sum sequence x squared plus 3. By the way, on your calculator, if you have one of these, you can scroll up and hit enter, and you can just change what needs to be changed. If you don't have one of these, you can hit second enter, and the same thing will happen. Okay, so sum sequence x squared plus 3, comma x, comma 0.5, comma 4, comma 0.5. Is that what you did? And you should get 37.5. So notice that these are the only 2 points that actually changed. That's the hard part. That's the part you have to ask yourself, okay, what's happening? I'm doing a left sum, a right sum. What's happening? Do second delete, and that'll be insert. And then you can insert it. Okay, I want to go over one more thing. So, if you're stuck, let me know so we can get you unstuck.
What is the catalog set?
That means if you want to get to the catalog, you do second 0.
Okay, well, I put in the original.
Oh, I got so many zeros. What the heck?
Is the second one for you?
Did you do? Okay, let me see yours. Because you didn't put the rest of the. Oh, the light is on.
Do I need to put a much?
What's our homework?
If it asks you for the midpoint sum on your homework, listen. Shh. If it asks you for the midpoint sum on your homework, you don't have to do that one. You can skip that one, and we'll talk about it tomorrow.